walks into a bar, and this teacher has a very high self-worth. And he goes and tells the bartender, okay, I'm gonna drink today until I overflow. And bartender serves him a single drink and he's done. You know why? Well, because he already had such a high value. It's just a weird joke. Anyway, I'm gonna skip the pleasantries, and if you're really wondering what this is all about, this is the Coding Interview Weekly with Lalit Kundu. Go check out the intro video if you are confused what's happening, and let's jump right into it. So the first problem that I posted for the week was this is like a typical interview problem that you may see, not the exact one. And this is kind of popular, but the point is not to delve into some sort of new problems, but explore the fundamentals as well as, how interview goes via some standard problems. It doesn't matter, right? So this is the problem. You're in a matrix and each cell has some coins on it. There are some rules of how you can walk through this matrix. From a cell that has a value X, you can only go to a surrounding cell around it if the value on that cell is greater than X, and it's strictly greater. So you can start from any cell, and the objective is to traverse as many cells as possible. So that's the question. And if you're reading this for the first time, I would say just pause the video, try it out yourself. And the most important thing is do capture your thought process, because that's going to be very important. Like, what are the possible approaches you took, and how you made sure that they're correct and stuff like that, because that's going to be important in an interview. And if you think you're done with the algorithm, the implementation part, you can figure it out later. Uh, try a follow where you have to find a cell from which maximum number of cells can be reached using the rules that we have mentioned. So that's how typically an interviewer would describe you the problem. And sometimes they would give you an example matrix as well, like this one. So in this one, if you take a look, the most optimal path starts at this cell 1 and goes to 2, 3, 4, 5, and 6. This is a path which has like 6 cells in it. You could try, like a different path, go from 0 to 2 or 2 to 3, maybe even 0 to 4, but these are not the optimal solutions because they're not the longest. Okay, over to candidate. So how do you start approaching this problem? Uh, there's one simple thing you can think of. Okay, maybe if a cell has the smallest value, it's kind of makes sense to start from that and see where we can land, because that will provide us the maximum number of possibilities. So, but you can see as in this example that 0 has the smallest value, but it does not necessarily, the most optimal path does not necessarily start from that cell. So what do you do now? I think most candidates would come up with some sort of a greedy solution where they start from a cell, try going in different directions if possible. And I think with most greedy solutions, you have to think, okay, if I am making a choice, how do I guarantee that it's optimal? So in this example, if you start from a cell and then you have two options to explore, which one do you really go into? And you know, uh, even a brief brute force solution can be provided to the interviewer where you say, okay, I'm going to go in this direction and then have some more options, like up to 4 options. And then I'm going to explore each of the option in detail until I can't make any more moves and record the length of that option and then backtrack to the previous option and traverse and look at the other possible options. So this is essentially exploring all possible paths in the matrix which are valid. This is kind of brute force, I would say. It's not even greedy. Now the question is, what's the time complexity of this? Is it efficient enough? And that is a very theoretical and fundamental problem in itself. What is the time complexity? So you are kind of exploring all paths in the matrix. So what is the number of distinct paths in a matrix? I mean, you can do a bunch of combinatorics and whatnot, but you can use master theorem. uh, but a way to visualize that is, okay, what is the height of this tree that we have made here, this whole tree. Uh, the height of this tree is total number of the longest path essentially, which is n plus m. And then on an average, what is the number of possible nodes at each of the levels, at each of the, and that's exactly, that could be 2 to the power of n plus m, because actually not even 2 to the power, but maybe 4 to the power n plus m, right? Which is kind of 2 to the power 2n plus 2m, which is asymptotically kind of similar. So it's a product of these two because that's the total number of nodes in this tree. And this is kind of a backtracking solution. Anyway, the point being, in an interview, you should never be afraid of exploring inefficient solutions. This exercise itself is going to give me so much insight into how you think, how you approach a problem. If you directly jump to a dynamic programming solution, I'm really going to be worried. Okay, do you already know this problem? Or how can you, maybe you just a person who doesn't explore simple solutions to complex problems, uh, you know. So it's important to approach negative solutions. And if you're going in a wrong direction, you might be worried, okay, am I gonna spend the whole interview talking about this inefficient solution? No. I mean, it's my responsibility as an interviewer to guide you in the right direction. So don't worry about time management. I'm very, if you're going in the wrong direction, most good interviewers would tell you, okay, this is not going to lead you anywhere. Let's come back and let's try something else. So that's the advice number one in this video. Never be afraid of approaching with your gut, because that defines who you are, not any number of different algorithms, stuff like that. Okay, so that's the whole backtracking solution. Now, what the greedy solution would be, and let me try to erase this stuff. Greedy solution would try to reduce the complexity of this backtracking algorithm from being exponential to something lower by saying, okay, I'm going to start from this cell, and if I have two options, I'll just choose one of them and discard the other one. And, you know, if I visited, some candidates would try to optimize this greedy approach by saying, okay, if I have explored one of the possible paths, I won't, one of the possible cells, I won't come back to it. But the truth is, any there could be any other optimal solution which would start from this cell and may utilize the cells that you've already visited. So it's all luck and chance. If you visited that cell, it's kind of wasted, and some other optimal path may have used it. So this kind of reasoning is very important from an interview perspective. It gives me an insight into, okay, you understand that you have a hint of how to prove greedy solutions. Like proving greedy algorithms is always really hard. If you are really interested, try exploring proving Prim's algorithm, which is essentially a greedy algorithm for building minimum spanning trees. They are hard, theoretically hard problems. But intuition wise, you have to say, okay, if I'm making greedy choices, I have to prove that if I had made any other choice, like there's no other choice which would lead me to an optimal solution, which is not true in this case, as I gave via a very high level intuitive example. So 10 minutes into the interview, I think we have to discard these two approaches, and I would facilitate that as long as you have your fundamentals right. Okay, so what happens next? Well, typically now I expect the candidate to move in one of two directions, which is, let's talk about the dynamic. There's a dynamic programming thing. They call it DP, and there's a lot of hula baloo around DP and how scary it is. I don't even know why somebody came up with that term. And then they talk about optimal substructure and all these complex terms. Uh, okay, it's not that complex really. So DP is, let's not even use that term. I don't want to scare people off. So you are trying to find your solution. Let's say, so the basic concept is this. You try to express your solution in terms of a recursive function, basically. That's the gist of it. So let's say f of I comma j, and I don't know, I think my laptop has just locked itself. Amazing. Perfect timing. Is it still recording? Okay, I think it is. So you say, okay, f of ij is my answer. And f of ij is basically the length of the longest path, which starts at cell I comma j. Then our answer is basically taking a maximum of this function over all cells, right? So how do we find f of ij? Like, what does it really depend on? So we have to think in terms of developing a recursive function. So from I comma j cell, you can go to some of its possible neighbors depending on what their values are. And you want to explore each of those options, right? If it's a valid move. So let's say you could go to only one of the possible cells just for simplicity, or maybe like two of those, I minus 1j and ij minus 1. These are the two possible cells that you can go to. Now, if you know answers for these two possible cells, we can just choose the better one of them and add one to it, and that's our answer, right? And this is a very basic recursive function. Now the question is, what is optimal substructure all about? What's that fuss? What's the fuss there? The thing is, we basically it's a very intuitive idea that we have covered all bases for finding, like we have for all paths that start on I comma j, we have considered all possibilities of where the second step of that path could be, right? It could be one of these two neighbors. So in theory, our solution is complete because we are considering all possibilities. And that's basically the optimality of the solution. Now, okay, folks would just uh, yeah, one advice I would go there when you're defining these recursive functions or like even defining the functions, you have to be absolutely clear about what f of ij denotes. You can't hand wave and say, okay, we'll define a DP function for cell I and then look at its neighbor, something like that. No, it's a theoretical problem, and we need to be clear while explaining. The communication aspect is really important here. So when you define f of ij, you have to mention, okay, f of ij denotes the length of the longest path that starts at cell I comma j. And typically in DP problems, you will define a function like this, f of I, j, k, l, blah, blah, blah. Then you need to say, okay, f of I, j, k, l denotes, uh, and it's an arbitrary example, it denotes that what is the length of the longest path that starts from cell I, comma j, and also goes through cell k, comma l. Or, like what is the number of possible paths of length k that start with cell I, comma j, and something like that. I think just be absolutely clear about the definition, because that's going to help you prove the optimality. So, and that's going to help interviewer know what your DP state is. So this thing is called your DP state. Now we have defined this function. You can go ahead and implement your own recursive memoization solution and everything. And what I would ask to these people, these candidates is, what's the guarantee that this recursive function implementation does not go into an infinite loop? If I define a function f of I equal to f of I minus 1 plus f of I plus 1, this is an infinite loop, because the answer for I depends on I minus 1 and I plus 1, and answer for I minus 1 depends on I, and so on. So this will go into an infinite loop, right? And this is not a valid DP state, because you're not expressing this answer for I in terms of smaller problems. You are just you have forced yourself into a recursive loop. So the Now that part, right, where I ask people, okay, why is this not going into an infinite loop? Is because from now that's an interesting part. Okay, it's not that easy. You can go to four different cells from I comma j. You know, I minus one j, ij minus one, I minus one j minus one, and so on. Not I minus one j minus one, but you get the gist. Um, that's where the graph part comes in. And let me erase this so that. So the question is, we are essentially expressing answer for a cell in terms of adjacent cells, right? And if it is a infinite loop, then we would start from I comma j, go to some of its neighbors, and like express our answers in terms of these neighbors, and then reach a situation where answer for a node depends on I comma j, right? And that would cause an infinite loop. So the question is, can this happen in our DP state? Uh, and that's where very basic insight comes into play, that if the value at cell the I comma j is x, then the possible paths that you're taking, the values for them will be greater than x. Let's say x plus d, x plus d plus d prime. And there's no way you can come back to cell I comma j because x plus d prime is certainly greater than x. So that's kind of gives me a hint. Okay, you understand why this DP solution works. And this is essentially the graph aspect of it as well. That's the other approach that candidates will take. So they will try to express the problem in terms of a graph. And how we do that is, okay, if I'm at cell I comma j, I'll express first of all, I'll express all cells as nodes in my graph, then add edges between cells, between adjacent cells, such that it's possible from it's possible to go from cell I comma j to its neighboring cell. So I've added an edge here, then this one, and so on. And the interesting thing we already know is that there cannot be a cycle in this graph. So it's a directed acyclic graph, right? Popularly known as DAG. Now, the problem is reduced to, okay, what is the longest path in a DAG? And all bakers for bakers and lead toasters know this is a very well-known problem. This is the first problem that they tell you when you go on these websites. And if you reduce it to this problem and then go and try to implement it, okay, what did they teach you? They'll tell, okay, topologically sort the graph and then do an iterative solution and stuff like that. Uh, if you go down that route, the implementation is gonna become very complex, while a recursive solution is much more simpler. So if you have that tunnel vision about reducing the given problem into one of the most popular ones that you have already solved, you may run into issues because you are now taking a longer route to solve the same problem. And it will also give a hint to the interview that, okay, you have solved a bunch of problems, and uh, you're trying to reduce things into well-known problems, and not, maybe you don't understand the fundamentals. So that's a advice I'll give. Okay, uh, try to explore the problem which is there, and take a fundamental approach instead of saying, okay, I know that problem, so I'll reduce it to that and then solve it. That may cause some issues. I mean, reduction is an important step while solving problems, but not at a high level. So that's the advice I would give. Anyway, so in this case, again, can you see a equivalence between finding the longest path in a DAG versus the DP solution we had made? It's the exact same graph. So dynamic programming is nothing but a directed acyclic graph of states. And you're basically traversing the DAG to find a solution. So in this case, I mean, recursive solution you can implement much more faster, even if you're expressing it as a DAG, and it helps you understand. Anyhow, let's assume the candidate does their coding and all really well. Um, if it's a really strong hire or a higher candidate, I expect them to finish this within half an hour, like 15 minutes remaining for the follow-up. Okay, my laptop keeps shutting down again and again. Maybe in the next video I'll fix this. So the follow-up that I ask is, and there's a reason I'll tell you why I ask this. Now the question that I ask is, find a cell in the matrix from which maximum number of cells are reachable. So in this case, from 0, you see that you can go from 0 to 4 as well as 2 and 3. So, and yeah, I think, and you can also go to 1. So 1, 2, 3, 4. 4 cells are reachable from 0. Whereas from 5, only 1 cell is reachable. And the reason I take this, ask this follow-up is it's a tactical shift from how you've been thinking. If you've been thinking about it as a dynamic programming solution, typically candidates would try to enhance their recursive function by adding more information to it, and that's a trap. So you had defined f of ij equal to blah blah blah. Now you're saying, okay, let me try to let me try to define f of ij differently, saying that, okay, f of ij denotes the number of cells that are reachable from I comma j. So you have cell A, you have B, that does not look like a B, but yeah. And then you have cell C and D. Okay. Yes. So now if I'm trying to calculate answer for cell A, this is a D. Answer for cell A, I'm going to say, okay, let's see what cells are reachable from B, and then what cells are reachable from C, and they might be disjoint. So I'll just sum them up to say, okay, this is the number of cells that are reachable from A. So you will say f of A equal to f of B plus f of C. Pardon my handwriting, I haven't written stuff down in millions of years, plus one for the cell A. You see the flaw in this? I mean, you are overcounting D. You have counted D twice. And that's a trap. That's trap number one. Okay. Let's say a candidate starts with this. I can probably give them a hint where they're going wrong. How they try to enhance this is by adding more information to the state itself. Saying, okay, let's say I maintain a bit set here of size n into m, and it has zeros and ones, and it basically is maintaining a set of nodes that are reachable from cell I comma j. And then I can do a bitwise and. So to express that more clearly, the new function would be, and it's not technically incorrect. And first, let me explain what the function I'm suggesting is. Okay, so f of I comma j comma mask. So bit mask is, we represent it as integer sometimes. This is defined as, okay, yeah, there's a challenge there. How do you define it? We can define it as true or false. It's true when the reachability set of cell I comma j is equal to mask, right? And then I'll go to its neighbors and say, okay, let's say it's I minus 1 and j. It is only one possible neighbor. Then if, okay, I keep messing this up. Let's say this value is true. This value is true. Then I can do an and, okay, and let's say I minus 1, j, not I minus 1, but like ij minus 1, comma, mask 2. Let's say these two values are true. That means I can take an AND, a bitwise AND of mask 1 and mask 2 to figure out the reachability set of I comma j, right? And then I can add that bit for I comma j as well and mark it as true. This is this is super complex, it took me a while to figure this out as well. So that's again one more trap where you're trying to enhance your existing solution and you're not taking a tectonic shift into the approach. It's technically not incorrect, but it's complexity wise pretty bad because um, the total number of states is n into m into 2 raised to n into m. So it's kind of exponential that way if you try to implement it recursively. So the point being, like all this complexity is not needed. It's very simple, start start fresh, and it's very simple. Uh, you have to think in terms of a DAG again. You start with a cell, okay. You have a DAG, okay. Let's try to solve it for one cell, and when we solve it for all cells, we can basically take the maximum one, right? Now, how do you solve it for a single cell? Let's say it's this one we're trying to solve. So you basically start a DFS from the cell and start exploring the whole graph. And you don't have to visit a cell again, and you will be guaranteed to visit all the reachable nodes from this set. So that DFS is very simple to execute. It's just order of n into m, right? And then you do it for everybody. So that's basically n square, m square. And that's a pretty good solution, This is what I would be looking for. So I don't expect somebody to implement this, in the remaining 5 minutes, 10 minutes, we can just discuss the algorithm and that should be pretty well enough to get them a higher or a strong higher rating. Uh, of course, like how you implemented the previous solution is important as well. So I hope this kind of helped you make a sense of what dynamic programming is and how it relates to graph. And you know what else can I mention? Implementation is important as well. So you can try implementing it. I would certainly like to help you out, figure out, okay, what's the best way to implement it. I think a recursive solution with memoization is best. Yeah. So hope you enjoyed this. I'm gonna post the next week's question soon after this video on LinkedIn. So keep an eye out and feel free to ask me more questions in the comments, and I'll be happy to um, explore them in more detail. So that's all. See ya next week.